Boa tarde, good afternoon to everybody, and it's a great pleasure to have Silvia Bonoli today at the seminar of the Valongo Observatory. Silvia will tell us about JPAS and the mini-JPAS survey that recently has been released and the paper has been published. Silvia is the first author. And Silvia got her PhD at the Max Planck Institute for Astronomy in Munich. And then she's been a postdoc at the University of Zurich and Stanford University before joining the Centro de Estudio del Cosmos de Aragón in Spain as staff member. In 2018, she moved to San Sebastián as an Iberbasque Research Fellow. I hope I said it well, Silvia.
Yes.
And now I leave with you the talk, the space, and thank you for accepting this invitation.
Thanks a lot, Arianna. Thanks a lot for inviting me. It's a great honor, and I hope you can all hear me well. So I'll try to share now. We had a bit of problems when we were trying before, so I hope things will work out okay. So let me give it a try. Okay, I think you should be able to see. All right. Do you see?
Yes, it's perfect.
Okay,
so
great.
I'm gonna go out and leave you.
Okay. Yeah, just interrupt me if at some point things are not showing up properly or you cannot hear me for some reason. Okay, so yeah, let me start then. Well, again, thanks, Arianna, and thanks all of you for joining today. Yes, as Arianna said, I will tell you about JPAS, and but in particular, actually, I will talk about mini-JPAS, which is a little project that was carried out in preparation of JPAS. Before I start, actually, let me mention a bit of advertising of the institute where I am at the moment. Is called Donostia International Physics Center. Donostia is the San Sebastian in the Basque language, here in the north of Spain. It's a physics center that recently opened a new branch in astrophysics. So if you're ever around in Spain, in the north of Spain, you're most welcome to visit. If you're interested in black holes, in dwarf galaxies, we actually have a meeting organized that was supposed actually to happen September last year, and for obvious reasons we all know it was postponed to September of 2022. So just keep it in mind in case you're interested in this topic. Okay, so let me move on talking about JPAS, and well, I'll start actually with a bit of background on why we are carrying out this. We carry out this big survey. So I start with this picture, this image that many of you probably have seen many times, dozens of times. We might be a bit bored by it, but actually it encompasses, it encloses most of our knowledge about the universe. We know that the universe started with what we call the Big Bang. There was a rapid expansion, an inflationary phase. Then we have this amazing cosmic microwave background that tells us so much about the early universe. Then a period of dark ages. And then finally, when the universe started ionizing, it's where the first also stars were forming and the first galaxies and so on. And then the universe started to develop and became the mature universe we see right now. So we have this really good picture. And in fact, if we put together all these ingredients, so what is initial condition based on the CMB, and the basic physics like general relativity, and this picture of the cosmology, which is given by the CMB, cosmic microwave background, which is what we consider a lambda CDM, a cold dark matter universe, we actually can get out, if we put all these ingredients in a computer and run some this example and body simulation, we get a distribution of structures that very much resemble the distribution of structures that we see in our sky, right? This is another example. This is the Millennium simulation, one of the most famous dark matter simulation. These are the simulation's output, the distribution of structures, of cosmic structures, compare with the distribution of cosmic structure of structures observed. This is quite old now. It's about maybe 20 years old. This is the 2DF and the Sloan Great Wall, some structures, some important big structures that have been observed. So the two, even just by eye, resemble a lot each other. And even if you do a quantitative study, they pretty much resemble the observed distribution of structure, and the simulated one really resemble each other. But going even further, in the last, a couple of decades, also our understanding also of the baryonic component of the universe has been improving. And also, if we put in a computer all our knowledge about how baryonic processes, all the processes that describe baryonic physics, like star formation, feedback, and so on, we can get out of our simulation, out of our computer, we can get out beautiful images, really realistic galaxies that, in many details, really start resembling extremely well galaxies that we observe, real galaxies that we observe with telescopes. This is an example of one of the most recent one, the TNG simulation, which really, it's quite amazing what are the details of, for example, these spiral galaxies. However, there are still many questions. Things are not really settled. Now, we have this very nice description of the universe from really early stages down to the galaxies in our nearby universe. But there are many details that, well, not quite details, actually. We still don't know what is the nature of cosmic acceleration. We still don't know what dark matter is made of. We don't know also if cosmic acceleration is due to any modification of general relativity. And also, if we go to smaller scales, there are still also many open questions in galaxy formation. Going from the early universe, details of really how ionization happened, all these processes of quenching, feedback, how supermassive black holes, how they formed, how they came to be, and how they affect in details the galaxies where they live. These are all questions that we still need to answer, right? In particular, so all these cosmological questions in particular have been driving a lot of investment from the community, from the international community, and a lot of surveys have been carried out, are currently working, and are planned for the future. And this compilation that I put here is by no means complete. There are many more projects that are, that are ongoing or have been planned. Most of these projects can actually be divided broadly into big categories: photometric surveys and spectroscopic surveys. Photometric surveys have the advantages that, so it's effectively just pictures or images of the sky. They have the advantage that they give unbiased samples of galaxies, and they're quite fast and therefore also cheaper to carry out. You can probe larger volume because you can go deeper. And so the cosmological volume that you're probing is actually larger, and you don't have issues, for example, of fiber collision. So therefore, you have higher number density of sources. But the information that you have on the individual objects is actually less detailed, right? And that's why other projects prefer to carry out cosmological experiments in which you need to know very well also the information, the properties, the distance to objects. And that's why other surveys, spectroscopic surveys other surveys prefer the spectroscopic approach, in which you really, you take a full spectra of a galaxy. So you know exactly what's the redshift of the galaxy. So for some type of experiments, like the baryonic acoustic oscillations, effectively doing a mapping of the sky in 3 dimensions, so on the plane of the sky, but also in the 3rd dimension, which is like the redshift dimension, this is the preferred way to go, because you really need to know the precise redshift of galaxies. These photometric surveys have been used, for example, this is a nice example here in the bottom left, about weak lengths in mass maps. This is from the DS science verification data. So there is something in between, which is the spectrophotometry approach. It's effectively like, it's mixing the two. So you're taking imaging like photometry, but with so many filters, and there is this sketch here on the right. I hope you can see my mouse. But with so many filters that you effectively have a low resolution spectra for the objects, for all the objects that you are taking a picture of, Okay, so you can have detailed information about the object, not quite as precise as with the spectroscopy, but good enough that you can do a lot of things, as I will tell you shortly. This approach, it's not been, it started, there have been already projects that were using this approach, the spectrophotometry approach, like starting from the Combo 17, Shards, Cosmos, famous Cosmos, Alhambra. But, it was very difficult. So these were all like pencil beam type of surveys, because to scan large areas with so many filters, it's very time consuming. So what you need is actually to have you need a very large camera, a telescope with a large field of view, so that you can image large patches of the sky at once. That's when this approach becomes effective. And one first example of this is the PAU survey, which already has, I think, a few tens of square degrees, which is already imaging with with 40 filters, interesting parts of the sky. The purpose of JPAS is to bring this whole approach to, let's say, the next level, to really a cosmological survey, like a large-scale survey, large area survey. So in a nutshell, JPAS, what it is, it's a multi-band, 56 filters, wide. Many times we aim at observing many thousands of square degree, the spectrophotometric survey of the northern sky. It's a collaboration, it's an international collaboration with the members from many different countries, but primarily it's a collaboration between Spain and Brazil. And the 4 funding institutions are, in fact, 2 in Spain and 2 in Brazil. CEFCA and IAA in Granada from Spain, and Observatorio Nacional and the IAG from Brazil. So let me tell you a bit more about the details of the setup of the survey. The most interesting thing about the survey, it's really the filter system, right? That's the unique thing of the survey. So the filter system of JPAS consists of 54 narrow bands of a full width of maximum 145 angstrom, overlapped so that they are spaced by about 100 angstrom. And then they're complemented by 2 broader filters in the wings, in the blue and the red wings. So this effectively delivers a pseudospectrum of a resolution of about 60, if you're familiar with how typically resolution of spectra are defined. And so this delivers a pseudospectrum for every pixel of the sky that this survey is going to observe. And this brings to photometric redshift errors, so like accuracy of redshift, which is the errors low as 0.3%. So we will know, we can get redshift for many sources which have a precision of 0.3%, okay? So this is really like a couple of thousands of kilometers per second. The survey will be carried out by a new observatory that was built 10 years ago in this mountain. There was nothing. This was built really in the last 10 years. This is a very dark region in continental Spain. So this is a map of Europe. There is a very dark spot, and this is where this observatory was built at about 2,000 meter altitude. It's a quite good spot, particularly good in particular for being in continental Europe, which made also the building and much more efficient. It's much easier than in a remote island or so, or in a very remote place, right? So the observatory has two main instruments: the Javalambre Survey Telescope, which is the main telescope which will be carrying out JPAS, and it also will be carrying out an observation in the G band for Euclid, and a smaller telescope, the Javalambre Auxiliary Survey Telescope, which is carrying out another survey called J+, which you may have heard of because there is a twin survey, S+, which is carried out in Chile, in the southern hemisphere, and it's a project pushed by Brazilian institutions. So these are twin projects, let's say. They have the same type of telescope, same camera, and same filter system. So just so that you know about the northern version, so S plus is the one in the southern sky, and J plus in the north. J plus has now, about in October last year, more than 2,000 square degrees of data were publicly released. So if you're interested also in this data, these are with 12 filters, so that you know that there is also this data available. So this is how the field of view compares between, this is the field of view, let's say, of the small telescope, and this is how it compares the one of the big telescope, the one of the camera that will carry out JPAS, and this is how it compares with the moon. So they're really, really large field of view instruments. The main camera, JPCam, it's a 1.2 gigapixel camera, consists of 14 CCDs, as you could have seen here. And on top of each CCD, there will be a filter, a different filter. The resolution is 0.23 arcsecond per pixel, and the entire field of view is 4.5 square degrees. So what I was saying earlier, this project, this spectrophotometric approach is really become feasible because large field of view instruments have become possible. So as I said, this is so all the filters will be distributed in different filter trays. So there are, as I said, 14 filters every time that will be on top of the 14 CCDs. And like a jukebox, one tray will be on top of the camera, will be observed, and then will be removed, and then another tray will go on top of the camera to observe with the other filters. This is the distribution. Below here you find the distribution of the filter in the trays. What's more important here to point out is the depth, the expected depth. So we expect for the narrow band to get to about 22.5 in magnitude. So that's approximately like Sloan, but with all these 56 bands. Then the survey will also be complemented with broadbands, and these will go a bit deep. Will go deeper. We expect to get to 24 at least in magnitude. So this is the footprint for JPAS. It's carried out in the north. So it will cover most of the northern hemisphere, and this is very much overlapping with most of the Sloan, the SDSS footprint. Sorry, this is a bit small, but approximately this right here is the SDSS footprint, and the JPAS one, sorry, will be a bit at higher declinations. Okay, so all the data processing and storage, we expect to get about 1.3 terabyte of data for every night of observations, and all the data processing and storage will be carried out by CEFCA, which is a research center close to the observatory, which is really pushing, which has been responsible for building the observatory and also for managing all the data process and so the data handling and so on. So what will JPAS do in terms of cosmology? So there will be, the typical four. Sorry, I should turn off here. I forgot to turn off my phone, which I cannot find. I hope this doesn't bother you. I don't know where I put it. Right here. Sorry, I apologize for that. There will be the four main cosmological experiment, type 1a supernova, clusters, clustering, and lensing. Let me focus on them and what JPAS can provide on each of them. So the main one will be clustering, so the study of the distributions of galaxies in the universe in 3 dimensions, so not only on the plane of the sky, but also in the redshift direction. So we expect to get, by the end of the survey, of the order of 90 million galaxies with exquisite redshift precision, with a precision of, as I was saying, 0.3%. So really precision that allows you to do 3D clusterings. But this will also be complemented with 2 million quasars and hundreds of thousands of Lyman alpha emitters to study the high redshift universe. But there will also be many other galaxies, many other objects with lower redshift precision, but that can also be interesting for both cosmological studies and also studies of galaxy evolution. We expect to have, with, for example, a 3% redshift precision, almost 500 million galaxies. these are just some, actually a bit outdated now, some forecasts also for how well JPAS will do compared with DESI in Euclid in estimating the Hubble parameter and the angular diameter distance, the errors. So we expect to reach the few percent errors and similar, in each individual, for each individual. So these are red galaxies, green using red galaxies, emission line galaxies, and the blue is for quasars. So for each individual, if we only focus on one individual type of target, one individual kind of object, so if we only focus, let's say, on LRGs, luminous red galaxies, JPAS cannot do at the same level of other surveys, but JPAS has the advantage that it doesn't pre-select sources. So we have all kinds of galaxies together. So you can put all these different tracers, what we call them, all these different galaxies, each of them is tracing the large-scale structure, and then its strength is when it's combining all these different tracers together. That's when JPAS really can do very competitively, also compare with spectroscopic surveys. Talking about quasars, also JPAS will be very competitive at high redshift, which is actually where quasars can be selected at best, as I will show you later, because thanks to the broad emission lines of quasar, we can detect them, both detect them and also detect the redshift very accurately. And also we have this joint project with WEAVE, which is a spectroscopic survey that will follow up 500,000 quasars selected in JPAS at high redshift. So with also this spectroscopic follow-up, we can really push what is the analysis of cosmological analysis at high redshift. And actually this probably combined, JPAS and WEAVE, will, are arguably possibly the most competitive project for the cosmological studies above redshift 2.5. Another very interesting topic for JPAS is are clusters. So because of the very high quality of the redshift, it's actually much simpler to detect clusters with JPAS. So these are some forecasts, from Ascaso et al. In 2016, which estimated that the minimum mass with high completeness and purity would be about of the order of 10 to a few times 10 to the 13. And this is actually the expected number density of the number of clusters that will be detected as a function of redshift for different surveys. And JPAS really sits at the same level of other experiments like eROSITA or LSST. And despite being much less deep, for example, the LSST, the advantage again of JPAS will be the high accuracy in the photometric redshift. And here I want to highlight also there is another very interesting synergy with eROSITA. So we have an MOU with the German side of eROSITA. We have an overlap of about 2,000 square degrees. So it will be quite interesting also to combine all different mass estimates from the optical richness that will be given by JPAS with X-ray and also lensing information to study and carry out cosmological experiments with clusters. The other two interesting topics are lensing. So we hope to carry out lensing experiments using the broadbands observations that will be carried out in the best nights. And also, again, the redshift precision will be very useful to separate lenses and background galaxies. Type 1a supernova, we don't have a specific program for Type 1a supernova at the moment. We had planned some cadence exposure to detect supernovae, but we're still, that is still pending. It's not obvious that we can carry out for just the way that the strategy of the observation will work. But still for supernova that we can detect, what will be interesting is to characterize the host galaxy, and we already will have the redshift again from the narrow bands, and we can characterize with the narrow bands the properties of the host galaxy. But also for galaxy evolution, this all extremely large statistic and all kind of galaxies, because there will be no preselection. So it's, JPAS will be quite useful for galaxy evolution study. Also, another interesting topic, as I will show you also in the examples with miniJPAS, will be to study nearby galaxy in an IFU-like approach, so study the spatial variation of the properties of nearby galaxy. But also, if we get closer, galactic science can also take advantage a lot from the data we'll have. So characterize all sort of type of stars, the physical properties of stars based from this pseudospectra, as we call them, that we will obtain. The study of dwarf galaxies, of satellite galaxies, of the Milky Way. In the north, as we will get deeper and we'll have more color information than SDSS. So we can go one step forward compared to SDSS in the northern hemisphere. And other projects like tidal streams, also another very interesting one is to find ultrametal pulse stars, which are very difficult to find with broad bands, and they're very rare, so it's very difficult with spectroscopy. But with this our spectrophotometric approach, we can actually find candidates that will need spectroscopic follow-up, but it will be very efficient to find candidates of metapulse stars. So what is the status of JPAS? So JPAS was supposed to be started already now, but we had also some delay due to the pandemics as well. So the main instrument, JPCam, was installed on the telescope in February last year, and saw the first engineering light, technical first light it's almost a year now, in June in 2020. This is a very nice image of Andromeda, and you see also the large field of view of the camera. And it's currently in commissioning, but the pandemic created some problems in the speeding up of the process, so the camera is still commissioning. But before JPCam arrived, we had an interim camera, which we called Pathfinder, much smaller, just the equivalent of one CCD, with which we carried out some interesting experiments to have some first data to play with. So we observed different parts of the sky, but we devoted most of our energies on 4 pointings along the extended growth strip or AGES field, which is a quite well-studied field, cosmological field in the northern hemisphere. And these 4 pointings that are covering almost the entire EGS stripe, they were observed with all the 56 JPAS filter plus the broadband UG-RNI. We dubbed this field miniJPAS. These observations, we call it miniJPAS. And I'll spend the rest of the talk telling you about this project. So this was a summary of this project. miniJPAS is contained in this paper. So this is again the footprint, and this is an image of it. So this is a color image of the stripe, and this is a zoom. This ABC are zoom in some interesting area where you can find some also nice big galaxy. So this is the data were released publicly at the end of 2019. And actually, if you're interested, you can go to this website. It is publicly available, and you can do all sorts of things. There is a sky navigator. You can search for object, do an object search, cone search, and also download all kinds of data via IDQL data search. So just to give you an example, so this is how the whole stripe looks like in the sky navigator. Then you can get closer, and you have all these points that indicate where objects are, and you can click on any random of them. This is just a random one, and you can get out what is this pseudospectrum, and then you can get more details about the object. This is just a random galaxy, and so on. And you can get out the photometry, all the information about the morphology, and so on. You can also search NED and SDSS for other information about all the objects that are contained in the field. So a bit of summary of the data. In total, it's 1 square degrees. So, really much smaller than what JPAS will be, but it already gives an idea of the power of the survey, right? Because already in only this 1 square degree, so even less than 1,000 of what JPAS will be. We have about 65,000 objects selected in the R band, and a total of 600,000 objects selected in the individual bands. So you can imagine that you have some objects that are faint, but I have some emission lines that are only come up in some individual bands. So you can find these objects also, these objects that are extreme emitters, that one would call them. These are also available in the catalogs. The depths are a bit inhomogeneous because for various testing reasons, we included a lot of different exposures in the data, but approximately our goal was to get at least as deep as JPAS, and in some filters, this is the depth. In some filters, we also reach deeper magnitudes. The quality of the sky during this observation were not always great, but we still have a full width of maximum of between 1 and 1.5 arc seconds in the narrow band and below 1 arc seconds in the broad bands. So still the quality of the image is still quite good for most studies. This indicates the number density of sources per square degree as a function of magnitude. As expected, in bright magnitude, you're dominated by point-like sources. So we have several hundreds, thousands of stars. And then as we go to fainter magnitude, we are dominated by extended sources, so galaxies, and we have, tens of thousands of galaxies in the field. And our completeness is estimated to be at magnitude 23.6 for point sources and 22.7 for extended ones. So let's get to actually something which is visually also very nice, is actually to look at the photospectra. These are some examples. So these are stars, some stellar objects. This, for example, a cataclysmic variable, a white dwarf, and we get to redder stars here. And you can find some, you can by eye see some absorption line features. For example, here it's very well traced, this absorption line. These are the points are our photometric data, and compared with the Sloan spectra in gray. And so you can see that the two follow each other. And and already with this, despite the low resolution of our spectrophotometric data, we can detect the major absorption or emission features. These are examples of galaxies of extragalactic objects, galaxies and quasars. This is an emission galaxy in the local universe. This is at redshift 0.1 almost. This is H alpha in emission. This is a red galaxy. You can see the 4,000 Armstrong break, typical of red and quiescent galaxy. And again, this is an emission line galaxy, a bit higher redshift. Another red galaxy is a bit higher redshift. And here we go, these last two examples are at high redshift quasar. So this is our quasar at redshift 1.7. This is one at redshift 4.2. And in particular, so C4 quasars that have broad emission line, so they are very well traced by these narrowband filters. So the detection and the redshift determination of quasars is actually quite easy with this kind of data. So what is the photometric redshift accuracy? Does it actually, really reflects what were the expectation? So this is a typical photometric versus spectroscopic redshift, and the vast majority of sources are within the one-to-one relation. This is the typical error, the way the errors for redshift is estimated. So that our target for cosmological studies, as I said, was about 0.3% in the error of the redshift. So this is reached. This is achieved for about 30% of the objects, down to magnitude 22.5 or so. But for all the objects, so these different lines indicate different completeness of the sample. For all the objects down to 22.5, we have below 1% redshift accuracy, so very high redshift, very high precision in redshift. This is dividing the sources into red and blue galaxies. Red galaxies have always quite good accuracy in photometric redshift, also independently on magnitude, whereas star-forming galaxies have a redshift accuracy that decreases with magnitude. So as you go to fainter sources, you have less accurate redshift as expected. But still, again, they are always below 1% in redshift accuracy. And let's see then what is the large-scale structure. How do we trace the large-scale structure? This is a slice of the field across through redshift. It's a slice redshift. The blue dots are the spectroscopic sources that have. So these are deep 2 from the survey deep 2 in the field that are already known galaxies. And on top of them are the orange point, which are galaxies from miniJPAS. And their color, the shades of the colors depends on the quality of the photometric redshift. Sorry, Isabella. Sorry. Chiudi la porta, Chiudi, Isabella. Sorry. So as you get to higher odds, it means that higher quality photometric redshift, right? So you can see that the galaxies trace, the miniJPAS really follow the structures of galaxies that, in this case are indicated by the spectroscopic redshift. And in particular, if you cut, you have this proxy for redshift precision. If you cut your sample to have only the highest quality photometric redshift, you really get the highest, you can really trace the cosmic structures. This is the number density of galaxy that we expect as a function of redshift. These squares are for all objects in miniJPAS, and the circles are for objects with good odds, so this proxy for redshift accuracy. So if we cut our sample in order to have the best redshift accuracy, of course, we reduce the number density of objects, but it's still comparable to the number. It's comparable to the number density of objects that, for example, is expected for DESI, and it's in the more local universe up to redshift 0.6 or so. It's higher actually than most other surveys that of the local universe. Some other example from miniJPAS. So just to give you an idea of the different kinds of studies that can be carried out. One thing I was mentioning before is this 2D studies, IFU-like study of nearby galaxies. These are so to study the spatial variation of the properties of galaxies. So how how the different physical properties of galaxies in different parts. As you move, for example, from the center to the outskirts of the galaxy. Or, if you do a morphological first selection, how the stellar population, for example, in a bulge or in a disk, how they compare with each other, right? And also as a function of environment. So this is the pseudospectra, the red points of JPAS, compared with the ones, the gray lines are from a spectroscopic survey. In this case was MANGA. Maybe you've heard of it. This MANGA is this IFU spectroscopic survey, and they're really overlapping, and the intrinsic properties of the galaxy that you can select are similar than the ones that you can derive from the spectroscopic survey. Now, of course, you don't have the same level of details, but the general overall bulk properties of different parts of the galaxy that you're selecting are similar from a spectroscopic compared with our photometric data. The advantages of JPAS here is you lose a bit in resolution, but the advantage is that you have a larger field of view. So, for example, MANGA is this hexagon. This is the field of view of MANGA, of the parts of a galaxy that MANGA can select. Whereas with JPAS, you really don't have a limit, right? Because you're taking an image of the full sky. So you don't only have the galaxy that you're studying, but you can also, so you can study a galaxy up to larger radii than what a spectroscopic survey would do. but you can also study that as a function of environment. See, for example, if there are satellites or so on. Another very interesting study, and this is where Arianna is working actively, is how the study of galaxy morphology depends on the color, on the wavelength, and how it optimizes the morphology characterization of a galaxy using all this different color information. This is again an example from the miniJPAS paper where you can see this, for example, a star-forming galaxy that you see, as you go to in bluer filters, you see, more the spiral arms, the activity in the spiral arms, and then, as you go to redder filter, you see different components of the galaxy becoming more important. There is already a paper published on miniJPAS data on, in particular, the characterization of the stellar population properties of galaxies across cosmic time. Is an example of a color mass relation, so where you expect down here to have blue galaxies, here red galaxies, and again you get results which are very similar, comparable to the ones that you can get with spectroscopic survey. And here the advantage again is that we can go deeper and to get to much smaller galaxies. So we can, I don't think actually I have here the plot where we have the mass, but well, actually no, yes, here we have the mass here. So you can see, that we can, especially at low redshift, we can get down to a few times 10 to the 8 in terms of the galaxies that we can study. Another interesting topic is the one of dividing star forming and AGN. So that maybe some of you may have heard of it, are familiar with the BPT diagram. So this is the BPT diagram, but done with our narrowband filters. So in general, you would need, spectroscopic, you would need to determine well the line width to classify, distinguish between star forming and AGN-dominated galaxies, Seyfert galaxies. But in these studies using neural network, this is a student in Granada, he has been able to find an efficient way to actually use the narrowbands to do this classification. So going to clusters, actually in Valongo, Paolo is also actively working on this, searching for clusters in miniJPAS. This is one of the biggest clusters in the miniJPAS field. In yellow here, you can see the only two galaxies that had spectroscopic redshifts. And these in white are written the redshift, the photometric redshift coming from miniJPAS. So this is a cluster that was not previously known. And thanks to all this photometric redshift, we managed to characterize it. An interesting study is the study of galaxy population within clusters, to study also how galaxy transformation within clusters. So this is another color mass relation, but where the objects here are color-coded from the distance to the main galaxy. So it's interesting to see what partially we expect, right? That galaxies that are closer to the center, so here blue, are actually redder. So the color coding is a bit counterintuitive, but are redder galaxies, whereas galaxies here in the main sequence of star formation, in the blue cloud, are actually further from the galaxies, from the center of the cluster, right? So galaxies that are at the outskirts of clusters are still actively star forming, whereas galaxies in the center have already been quenched. And this is a similar way to look at it by looking at the equivalent width of H alpha, which is a tracer of the level of star formation. So the lower the equivalent width, the more quenched is the galaxy. The higher means that the star formation is more active, and that's also what we find here. That galaxies that are here in the also that are blue are also have a higher level of have a larger equivalent width of H alpha. There is a paper in preparation with the catalog, with the cluster catalog of miniJPAS. Just to mention here, I go a bit fast. Just to mention that we reach this minimum mass that was expected. So really below 10 to the 14 solar masses, we are able to detect, so it's not anymore clusters actually, but there are groups of galaxies. So we can detect groups of galaxies. and also with a very good redshift accuracy. The redshift errors for the clusters are also of the order of about 0.3%. Just a few, just a couple of more slides, just to finish up. I'm particularly interested. My main research is on AGN and quasars. So, I just wanted to show you a couple of slides of things we're working on with AGN and quasars. So how do we do with quasars? As I mentioned at the beginning, quasars are quite good to be traced with JPAS because they have broad emission lines. So the photometric redshift accuracy, so these are all known quasars in miniJPAS. So we're working on determining their redshift, and they're actually, most of these papers are pushed by, this work is pushed by people in Sao Paulo. So they are trying to understand how well also we can determine the redshift of quasars. And again, we get quite good results, again, sub% precision in the redshift estimate. But we can even move forward a bit further. So what we're trying to do, given that we can estimate, we don't want to get only the redshift, but also we are trying to see if we can characterize quasars in more details. So, for example, here is an example, a first attempt to using QSFit, which is a free package to dissect, let's say, a spectra of quasars that was developed for Sloan. So we ran this package on our pseudospectra to get what are the different components of the quasar. So the different, the continuum, the different kinds of lines, the broad and narrow emission lines, and so on. This is a specific work that was done. This is a work in preparation. A similar work where we are trying to really fit and estimate the width of the emission lines for quasars to estimate black hole masses, because as you may know, there is it's called the single epoch mass estimate. You can determine the mass of black holes by first estimating the width of the broad emission lines. Another interesting things that we are doing for quasars, but could be extended to other kinds of objects, is actually to boost the spectral resolution by stacking our pseudospectra, which we actually call sometimes J-spectra. So here it's hundreds of quasars from MOCs that we have been stacking together, and it's compared with Vandenberg, which is a classical, so the textbook example of a quasar spectra. So you see that we can get a much higher resolution, much higher than what our narrowbands would offer, by stacking all these spectra, let's say J-spectra, pseudospectra together. And this is the last thing. Also, we can study, again, with this IFU-like approach, we can study nearby AGN, again, to study the effect of the active black hole on the properties of the host galaxies, but also, again, for more distant AGN, do spectral fitting of this and study the stellar population and the environment of AGN. And we expect to be able to do this up to redshift about 0.8 or 1. Okay, so I'm going to finish up here. This is just a quick summary. So JPAS is a multi-band, wide spectrophotometric survey of the northern sky. The main instrument, JPCam, is currently commissioning, and we really hope it's going to start, we can really start soon the survey. But in the meantime, we were busy with this miniJPAS data set, which is already, giving us a lot of data, gave us a lot of data to test all sort of pipeline studies and really prove that the potential of our data. And with this, I finish. Thank you.
Thank you very much.
I don't know what to do right now. Okay. Yeah.
The audio is a bit strange, but maybe it's my computer. So before opening up the question, I wanted to complement something I didn't say when introducing you that I think is very important, which is that you are one of the scientific director of JPAS, together with Renato Duque, and that also you are part of a committee of women in and astronomy in the Spanish Astronomical Society, which is something that I find also very interesting and important for us women, and as you were saying, it's not my case, but it's the case of many of us, mother in astronomy. So
yeah, as you could see, we get those interruptions. Yeah.
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 So, okay, I'm going to start with the first question that Pedro Enrique Cesar asked. And he subsequently commented that you kind of already replied to the question, but I will read it anyhow in case you have something to add.
Sure.
It's here. So, thanks for this great talk. Do you know if the JPAS filters will be able to differentiate the emission lines like the ones used in optical diagnostic diagrams?
Yes, thanks, Pedro. Yeah, that's really a good question. So, yes, I mean, I partially, I mentioned something, not very much depth because we didn't have time for it. But yes, so we expect to be able to carry out at least, at least in a statistical sense, right? So, object by object, you might have some errors, of course. But if you want to study large groups of objects, large group of galaxies, then yes, you can rely on these tools to differentiate between different kinds of emission, like between emission due to star formation or emission due to the central, the nuclear of the galaxy. Yeah.
Okay. Thank you. So the next question is from Douglas Brambilla, who is also co-organizer of the seminar here at Valongo, and is asking about saying a bit of the advantages and disadvantages of the pseudospectral in relation to the spectra itself.
Yeah, I mean, certainly, this pseudospectra cannot do all the things that you could do with a spectra, right? You cannot have a very accurate estimation of the, equivalent width to very accurate levels, or emission lines that are too faint to show up in these narrow bands, because there are some emission lines that they just have a too low equivalent width, so they would just not be detected, right? And the same goes for absorption features. If they're too weak, then they would not show up in JPAS, right? With our pseudospectra. But the advantage again is that you would have a much broader sample. And the statistic really, it's the advantage, right? And no pre-selection. So you can have a lot of different kinds of galaxies or stars and so on. And you're just limited by the flux, by how much the photons that your telescope is able to collect. So I think, these are the main advantages and disadvantages. Of course, it depends what you want to do, right? If you're really interested in some details of, whatever, like accretion disk of an AGN, down to the very, some understanding really details, some emission lines, then that you cannot do, right? But if you want to study, the general AGN properties, just to stay on AGNs, right, across cosmic time with a large sample that gives you some statistics and as a function of environment or as a function of morphology of the galaxy or so on, that then probably, this can be more advantageous than a spectroscopic survey. And also, being photometric, you generally can go deeper. So it's very difficult to reach the same depth with spectroscopy.
And maybe also it can be used to find objects that can be in a subsequent moment study with other instruments. Yes,
that's a very good point, Ariana. Yes. So, for example, I was mentioning these metal poor stars, right? So these J spectra will be very good to select candidates. Of course, when you want to study and confirm them, you will need spectroscopy. But, it's different to have, maybe 1 in 1,000 success rate if your pre-selection is only with broadbands, over maybe 1/10 success rate, thanks to the much higher precision, that much higher likelihood that your object is what you were looking. It's really what you were looking for. Yeah.
Okay. Next talk is from Jana Martins. That's a student here in Valongo as well. And she's saying, really nice project, Dr. Bonoli. What can be done with photometric toward composition. Can we use JPAS or mini-JPAS to study the astrochemistry of the sources?
I guess you mean for stars? Do you think? Yes. So I think there I'm a bit more ignorant, but yes. So what the stellar colleagues tells me is that you can estimate the composition, the chemical composition of all of the objects you're observing. Now, the exact precisions with which you can get and which elements you can get and with which precision, I cannot tell you at the moment. I don't remember exactly. And we still are actually, with miniJPAS, that's still an ongoing project. So it's not completed yet. But hopefully we will know soon as well up to which level we can do that also for stellar objects.
Okay.
Thanks.
Thank you. So then we have a question from Paolo that's asking, well, first of all, is congratulating for the talk, and then he's asking if there is a planned follow-up for supernovas.
Yes, that's a good point, Paolo. So that's still something we should discuss also again soon when we finalize the strategy. So the initial strategy for JPAS, the initial goal was to have 4 observations, 2 in the same nights, and then 2 in the subsequent 2 months. So that would allow to detect quasars independently in JPAS. Sorry, not quasars, supernovae. To detect supernovae and characterize them at the same time. Now, the problem is that observationally, that strategy is a bit dangerous because especially there are some fields that are observable only, for a couple of months in total. And then if you are waiting and if you're unlucky with the weather, then you don't complete observation in certain fields, right? So let's say that's not optimal at the end. So we are reconsidering, and the thing would be there are 2 things there. So compare our data with archival data to select, from other surveys to select possible candidates for supernova and then characterize them with our data. The other, there is this idea of actually using non-photometric nights, so the nights that cannot be used in which the sky is not as good quality to do JPAS, to use that to carry out variability type of projects. And then supernova could be one of them.
Okay, thank you.
Thanks, Pablo.
Okay, then we have a question from Karim that says, thanks, Silvia. It seems like a JPAS has great potential to create large samples of emission line galaxies like Greenpeace. Would you comment on it?
Yes, so I know that there are some people that are very interested in these. Select also this kind of galaxies that are, not very frequent. They don't have a very large number density, so they're difficult to find in spectroscopic surveys, which are, maybe only focused on some specific fields and so on. So yes, so we really hope that emission line galaxies from these Greenpeace or other kinds of emission line galaxies, at lower redshift or moving to higher redshift Lyman alpha emitters, all kinds of strong emitters, emission line objects, whether it's from the nuclei or from star formation, they can really be detected well. And then the goal is to get large samples. Maybe Arianna, you also want to comment on this. I know you've been thinking about that as well.
Yes, so one, now is a doctor that was part of the group here in Valongo, was actually was interested in looking for emission line galaxies at Greenpeace in JPAS. I remember that in the last presential meeting we had, when the world was more normal, we had a bit of discussion about this. And also remember other people, I think from IAA, were interested in this type of study. So I think it's something that we could, keep pushing forward to try to see if we find.
Yeah, right. Yes, and in general, that's the goal, to really get. So I think someone tried to look in miniJPAS, but the field was a bit too small for particularly particular kind of object. I think, for example, the Greenpeace, but we're selecting other type of emission line, trying to find other type of emission line galaxies. There is some work ongoing.
Yeah, because it's true. miniJPAS is just 1 square degree. So as you were saying, is less than 1,000 times of what the area we will cover.
Yeah. So
Okay.
Thanks, Karin.
Then we have a question from John Yana Galardo from IAG UTI, saying very nice talk. Can you please tell us if JPAS is planning to observe bright stars? I mean stars with magnitude in B lower than 13.
No. So there will be, so in the field there are stars that are bright and they just saturate, and they are just masked out, unfortunately. There is a project that is being carried out with a smaller telescope. I don't know actually what's the status of it. So actually, I forgot to mention. So the smaller telescope has already been open for open time, the one that is carrying out J+ with the 12 filters. And there has been a project, now I forgot the name. If you're interested, maybe, we can get in contact and I can tell you the name, to observe bright galaxies on the plane of the galaxy, right? So including the Milky Way, because the footprint of JPAS is a cosmology. It's outside the galaxy, right? It's trying to avoid the Milky Way. But there is a project with these 12 filters that have tried to look also and try to take different kinds of exposures so that also bright galaxies could be studied. And I think also S+ possibly is also as one program to look at bright stars. That's with the 12 filters. But at the moment with JPAS, with the filters of JPAS, that's not in the plan. But it could be asked for open time. That's actually something that could be asked for open time.
Mm-hmm. Yeah, that's interesting. Okay, I have a question. So, Mike, I have a question regarding what you were showing of resolving AGN in galaxies and in general detecting AGN in galaxies, because something that we have been discussing quite a lot is the effect the AGN could have on the decomposition of the galaxy light into bulge and disk component. So somehow I thought that we could use your detection to pre-select galaxies into galaxy with and without an AGN to be sure that our sample is actually clean. And then for the one with AGN, do a deeper study. But maybe we could use this to really know if the AGN is effectively somehow affecting the light. Yes.
Or at least, that's something actually, Arianna, that I wanted to talk to you about, because we are also interested to study this galaxy after a morphological decomposition, right? And I'm also wondering whether, if you know that there is an AGN and you know in which bands you expect most of the contamination from the AGN, whether you can somehow mask these bands when you determine the morphology of the galaxy. So you just use the bands where the stellar component is the one predominant.
Yes. Yes. Okay. And there is a question from Denise. So Denise is also saying, hi, Silvia. And she's suggesting if the PI of the Bright Star project is Alfaro.
Yes, he is. So maybe you know about the project, Denise. Yes, the name of the project just doesn't come to my mind. But yes, I think it's Emilio Alfaro, the PI. So maybe you know about it. Yeah, it's the one you have in mind. Thanks. Yeah.
Okay, Silvia. So we thank you a lot. There is already evening. So many people congratulated for the talk and thank you for
you. Let me also mention that again, this is Brazilian collaboration between Spanish and Brazil. So if you have some idea of some specific project or so on, talk to Arianna or contact us, and we can see also find ways to collaborate. Yeah.
Okay.
Okay.
Denise.
Thanks. Hope to meet you one day in person.
Let's hope one day soon we can meet again.
Yeah.
Okay.
All right. Well, thanks a lot for all of you.
Ciao,
Okay.
and thank you all. See you next week in the next seminar.
Okay. Thanks, Arianna.
Ciao.
Ciao.